Welcome to our demonstration on information-centric networking, ICN. So ICN is a future internet network technology that we in Cisco investigate and contribute to design, especially in the context of 5G. And the reason why is that it really simplifies the network architecture, either for fixed or mobile networks, by defining a network substrate as completely agnostic to the access technology. So you're going to see here that it's going to work on top of Wi-Fi, but the same approach is going to work over 4G, 5G tomorrow, etc. And the reason why we looked at ICN is that really rethinks the network architecture in a way that integrates some of important network functionalities that we today deploy as an overlay on top of the network infrastructure. So those functionalities are essentially three. So the mobility management. We're going to redesign and demonstrate, this is what the focus of the demonstration will be about, the mobility management in a way that is going to be completely anchorless. So we are going to remove the need for an anchor in the network core and really simplify the operations that are required from the network point of view to manage user mobility. The other functionality that really simplified and integrated with the network infrastructure in ICN is security. So here we are going to remove the connection between endpoints, and the security model is going to secure the object, the content, rather than the container, the connection between endpoints. And finally, the transport layer is much more efficient and completely different with respect to the one proposed by TCP/IP today, in the sense that it removes, as we said, the need for connection to be established between endpoints, but it's simply focusing on the data, which are going to be named. This is why we call information-centric networking. And the data are going to be requested by a unique known endpoint, which is the consumer, to the network. And as you're going to see, the network is going to be capable of routing directly based on the information. So let me guide you through the three major components that define the ICN communication model. So every piece of information, every content is going to be named. And with name, I mean identifiers that are location independent and really intrinsically related to the information that is carried. Then we have a network which is able to route based on name. So we have name-based routing. Every network router that receives a request carrying a name is able to route the request so that it is able to reach the first or the best hitting cache. And third, we have a transport layer that's enhanced, as completely redefined with respect to the one that TCP/IP defines. So we don't have anymore the need for instantiated connection. We only have a unique endpoint, which is the receiver, sending out requests to the network, and the network is able to route, to locate the content, and send it back to the user. So if you want to recall the communication principle of ICN, let's go through these 5 communication principles. We have named packets that are going to carry information about what rather than where, so they're not going to carry the information about the location of the content, because the user doesn't know and doesn't need to know where the information is stored in the network. So the user is controlling the communication by sending out requests to the network. So we have what we call a pool-based model, where the consumer is controlling the communication. And then every network router is able to do some operation based on these named packets. So it's going to look into its content store. If the content is stored locally, it's going to be sent back directly to the user. Otherwise, it's going to forward the request until a source of the content is located. And this kind of forwarding operation are taken in a hop-by-hop way, in a completely distributed way by every network router. Then when the content is located, it's sent back on the reverse path. So we have this symmetric routing principle in ICN that allows the data to be routed exactly along the reverse path of the request. And while doing that, every network router has the opportunity to cache the content for serve future requests. So in the demonstration here, we're going to see different capabilities of ICN. So let me just show you the setup of our demonstration. So we have represented here is a Wi-Fi access network using 802.11n. And we put ICN directly on top of layer 2, so there is no IP. And there is an ICN protocol stack on the mobile devices, on the access point, and on the backhaul routers behind. Now, let me just recall that we have used Wi-Fi, but the same approach is going to work for another access technologies. It can be 4G and 5G tomorrow. So we're going to see different parts of the demonstration that are going to use all the robot here, and what you can see on the monitoring tool is the different point of attachment. So for instance, if you have a mobile device that is going to switch from the access point 1 to the access point 2 to the access point 3, and again, this is what you're going to see on the monitoring tool. On the small one, you're going to see the traffic as well as on the monitoring tool in red from the server to the consumer device. Okay, so the first part of the demonstration is about consumer mobility and the way ICN handles consumer mobility. So we have a mobile device that, as you can see here, is going to request content to the server, and in red you see the data packets that are flowing back to the consumer. The video is displayed on the screen on top of the robot. Now, if the consumer, while requesting the video, moves, what happens in IP today is that the connection that you have between the server and the consumer has to be migrated over the new access point. In ICN, it is not the case at all. So as the consumer moves, it's going to attach to the new access point, the access point 2 in this case, and is continuously sending requests for the packet that he hasn't yet received up to the server. Here, what you can also show is that you have two paths, and the requests are going to be load balancing over the two paths using the available resources. What we have here is actually a load balancing strategies that is trying to minimize the congestion over the different paths. So as it moves, it keeps moving. You're going to see another handover over to the access point 3, and again, it's going to retrieve the content either from the intermediate cache, node 4 and 5, and up to the server. So as you can see, there has been no signaling, and there has been no degradation of the video quality while the consumer was doing the handover between the three access points. This is due to the fact that the communication is connectionless, so the receiver simply sends out requests to the network, and every network router load balancing the request over the available path, so that the content can be retrieved not only from the origin server, but possibly from the intermediate caches. So the second feature of ICN that we demonstrate here is asynchronous multicast. So the case where you have multiple devices, in this case it's going to be those two robots, that are requesting the same content, the same video in this case, up to the server, but not exactly at the same time. What we are able to show is that when the first consumer requests the content, as you can see, we have initialized the caches, so the content comes directly from the server and is cached along the path. Now, if a second consumer, the consumer here on the right, is requesting the same content after a certain time, without synchronizing the two flows, what you're going to see is that his traffic is going to be served directly from the access point, so the first hidden cache. This is particularly powerful. For instance, if you have a live event and thousands of users that are connected and more or less in the same time window are going to request the same content, what's happened is that without synchronizing the different flows, the first intermediate cache is going to serve and demultiplex the traffic to the different user, while a single flow is going to go up to the server to retrieve the content. If you think of the same scenario in IP, the way we manage multicast in IP requires really to synchronize the different flows. Otherwise, you're going to have thousands of flows going up to the server. Now, if you move the request for the second consumer forward, we're going to see this phenomenon disappear. This is the case now. So here, the sum of the flows is going to request and retrieve the content directly from the server because the different chunks are not already in cache. Now, as soon as the first user catches up and requests the chunks that have been already requested from the second consumer, you're going to see again this multicast phenomenon. So what's really important to remark here is that the multicast is realized by the intermediate caches without any signaling, without any synchronization of the different flows. And that's really a powerful feature of ICN. Now, if you go to the third part of the demonstration, it's going to be about multi-homing, the way you manage multi-homing, which is completely native in ICN. So here we have a single device, and for the moment, as you can see, it's connected to the Wi-Fi access network that we were using so far. So again, it's going to request the video up to the server. We've emptied the caches, so the request goes up to the server, and the data packets reach the consumer from the server through the network node 4 and the access point. Now, if another network interface becomes available, so it can be a Wi-Fi, in this case it's going to be another Wi-Fi access interface, but it could have been 4G, LTE, 5G, etc. So what happens here is that as soon as it discovers that it's connected to two Wi-Fi networks, that in this case are connected to the access point 1 and 2, is load balancing the request during the flow lifetime and without any degradation for the user quality of experience over the two network interfaces and up to the server using all available paths. So in this case, what we are using is a load balancing strategy that tries to minimize the congestion over the entire network. This is something that actually the service provider can tune, and for a specific class of service, for instance, you can decide that as soon as the device is connected to Wi-Fi, it's doing Wi-Fi offload. For another class of service, you can decide to maximize the throughput and so takes all available bandwidth over the multiple interfaces. If you think of what happens in IP to manage the different network interfaces, there is something that you would have done through multipath TCP. But actually in multipath TCP, you should have known in advance how many paths you want to load balance your request upon. And you should have known behind those paths where the sources are located. Here is completely native in ICN. So as soon as, for instance, the second Wi-Fi interface is down, so the mobile device is simply switching over all the requests over the available path, as you see on the monitoring tool, without any degradation for the video quality which is perceived by the end user. So the last part of the demonstration is about producer mobility. And here what we define is a mobility management protocol which is completely anchorless. So as you are going to see, the signaling is completely localized, and we're removing the need for an anchor within the network core to control this kind of mobility. So here what you have is a producer. There's going to be the camera mounted on top of the robot. This is going to move from one access point to the other, and while doing that, it's going to stream a video in real time that is recorded in the room here over a mobile consumer. So in the IP case, what happens is that this kind of mobility requires a global routing update, and it requires a complex operation within the network core to manage this update in terms of forwarding in the entire network. So here what we do in a few words, it's really simple. We have the producer which is moving, and it's also responsible for producing a given content. For instance, it can be named /p/camera real time. And as soon as it attaches to the new access point, the access point 2 in the slide, what it's going to do is simply send a short message with the name /p/camera real time to the access point to himself. So actually, the fact that he sent a message to himself, there has been no routing update in the network, means that that message is going to be routed to his previous location. So while doing that, all the intermediate routers can update their forwarding state, what we call a temporary FIB, forwarding information based, in order for the consumer request coming from the network core or from the access to be rerouted towards the new location of the producer. And this can be done, as you're going to see, in real time in a way that we are able also to support latency sensitive application. So we have here a mobile producer, which is the robot with a camera mounted on top. And the camera is going to record in real time the video of the room and streaming the video over to the consumer here. So you're going to see on the monitoring tool that the communication goes through the shortest path between the two, the consumer and the producer, and actually this is due to the mobility management protocol I was explaining so far. So now you have the consumer that is streaming the video produced by the camera. Now we can have the producer that now moves and is going to attach from move point of attachment from one access point. So far it's connected to the access point 1 as well as the consumer. And as soon as it connects to the second access point, as you're going to see now, what happens is that it's sending an update message, as we have said so far, between the access point 2 and the access point 1, so its previous location. So that every request coming from the consumer is going to be rerouted toward the new location of the producer without any degradation, any latency with respect to the quality of experience perceived by the end user. So now the same, when it's going to attach to the access point 3, this is what happens. So the shortest path, the path between the access point 3 and the access point to which the consumer is attached, is going to be updated by our interest update, so that the communication happens really following the shortest path. Okay, so now we can disconnect the infrastructure behind, so that we are able to show that all the communication is really localized at the edge. So there is no anchor in the network core and no communication, no signaling that happens with the network core. So this means that actually ICN can support mobility at the edge in what we can call an infrastructureless way. So it can work without any communication with the network core. So this happens, for instance, in a disaster scenario, which is one considered, for instance, in the 5G context. And there, the fact that you're able to communicate by simply using the communication at the edge, or between the access point, or really between the edge routers, that's really a powerful feature of ICN. So this concludes the demonstration. Thanks for your attention.